Today, we're diving into a concept that honestly feels straight out of science fiction, but is rapidly becoming, well, the bedrock of digital trust. Proving something incredibly complex is true without revealing how it's true, and doing it with, mind-blowing efficiency and transparency.
Yeah, it's the fascinating world of zero-knowledge proofs, and they're becoming absolutely essential, really, for building verifiable trust in our, well, increasingly intricate digital landscape.
That, without revealing how a cat part is, it's truly mind-bending.
It is.
But Stark's scalable, transparent arguments of knowledge, they promise to do just that.
Exactly.
We're going to unpack this powerful flavor of zero-knowledge proofs today.
So our mission really is to demystify Starks. We want to move from their core principles, the foundations, all the way to their real-world impact.
Yeah.
And show you why there's such a, well, pivotal development in computational integrity. Let's do it.
So how do Starks actually begin to solve this?
Yeah.
This seemingly impossible puzzle. It all starts, I gather, with how they transform the computation itself.
That's right. The core problem, like you said, is proving a computation was done correctly without revealing every single intermediate step or the secret inputs.
Okay.
And they achieve this by encoding computations into what are called algebraic execution traces. Now think of it as taking every single operation, every number, every step of a calculation, and mapping it onto a continuous mathematical curve, essentially a polynomial.
That's fascinating. So instead of just a list of steps, like 1, 2, 3, we're literally turning it into a smooth curve on a graph. Does that lose any information? Or is it just a different way of looking at it?
It's a different language, really, a more powerful one for this specific purpose. The beauty is that it doesn't lose information. It encodes it in a way that lets us use powerful polynomial properties for verification later.
Right, which you couldn't do with just the raw numbers.
Exactly. So to make this concrete, let's track a specific simple computation example. Think of a Fibonacci-like sequence. It's not just calculating numbers. We're using this sequence as a kind of stand-in for any complex computation.
Okay.
So the rule is n plus 2 equals on plus 12 plus an n2. Simple enough. We start with a0, and a1 is a secret value. Let's call it x. This x is the witness we want to prove exists without revealing it.
And the goal?
The goal is to show that after, say, 10,022 steps, the sequence reaches a very specific final value. A1022 equals 23387755057. And crucially, all these calculations happen in what's called a finite field.
Okay, hold on. Finite field. What's that all about? That sounds like something straight out of a math textbook.
It does. But in simple terms, just think of a finite field as a special number system. All the calculations stay within a fixed, manageable range. Numbers don't grow infinitely large. They sort of wrap around.
Okay, like modular arithmetic.
Precisely, like modular arithmetic. And this is absolutely essential for cryptographic proofs because it keeps computations predictable and prevents overflow issues, things that could break the system.
Okay, got it. So we've got our computation, our Fibonacci thing happening in this special number system. What's the very first step Starks take to actually encode this sequence into that polynomial you mentioned?
Right, so that's where low degree extension, or LDE, comes in. And this step, it kind of breaks down into 3 critical phases. First, the prover generates the input. That's the trace.
The trace, that's the full sequence of values.
Exactly, the full path of the computation. In our example, all 123 values of that Fibonacci-like sequence, from A up to A8 or 22.
Okay. Then, if I'm following, they interpolate these trace values. It's like finding the unique mathematical curve, the polynomial that goes through all those sequence points.
You got it. It essentially encodes the entire computation into that single mathematical function.
And then the extension part of LDE.
Yes. This is crucial. The prover evaluates this polynomial, but not just at the original points. They evaluate it over a much larger set of points.
Why larger?
Well, for our example, maybe a domain 8 times larger. So going from 1,024 points to, say, 892 points. This expansion, it's a bit like Reed-Solomon encoding, the kind used in CDs and QR codes. It adds redundancy.
Okay, redundancy for error correction, or?
Here, it's more about making the properties of the polynomial easier to check probabilistically later on. It magnifies any inconsistencies. The real insight is how LDE transforms this sequential computation into, well, a high-dimensional mathematical object. It lets us leverage these powerful polynomial properties for verification.
Something impossible with just the raw sequence of numbers.
Exactly.
Okay, so now we have this extended polynomial representation. What's next? How do you commit to it? This is where it gets really interesting, right? And where Starks start to differ significantly from, say, Snarks.
Absolutely. This is a key difference. Instead of relying on things like elliptic curve pairing operations for commitment, which many snarks use, Starks leverage cryptographic hash functions, specifically Merkle trees.
Merkle trees. So using hashing, is that the core cryptographic distinction then?
It's a huge one. It's elegant, really. This use of Merkle trees allows for simpler and, importantly, quantum-resistant commitments.
Quantum resistant, okay.
Yeah, and it still enables incredibly efficient verification later, even when dealing with massive computations. So, the leaves of this Merkle tree are basically the hashes of all those extended data points, those FXJ values we calculated.
Right.
The prover then calculates the Merkle root of this tree, and that root is the commitment. That's what the prover sends to the verifier first. It's like a promise saying, I have specific values at these specific points in the extended trace.
And the beauty of this Merkle tree commitment, as I understand it, is that the prover can later reveal just a tiny subset of values from that huge list
Exactly.
without sending the whole thing.
Yeah.
And they can prove cryptographically that the revealed value was part of the original commitment. Super efficient.
Incredibly efficient for proving data integrity without revealing everything. So, okay, once we've got our computation encoded and committed to, the next big challenge is ensuring it actually follows the rules, right?
Right. How do Starks take those logical rules, like the Fibonacci step, and turn them into something provable with algebra?
That brings us neatly to part 2. Defining and combining the constraints, the algebraic proof. For our example sequence to be valid, remember, 3 conditions had to hold.
Okay, let's recap those. Rules of the game. First, the initial condition of the 0 had to be 1.
Correct.
Second, the final condition. A1D or 2DO had to be that specific large number, 2 to the real 33, whatever it was.
233-877-5057. Yep.
And third, the step-by-step transition rule. L plus 2 equals min plus 12 plus N2. That rule had to hold for every step.
Exactly.
But how do you turn a rule like A0 must be 1 into a mathematical equation that a computer can actually prove? It feels like bridging 2 different worlds, logic and polynomials.
That's where arithmetization comes in. It's a clever process. Starks translate these conditions into polynomial identities using a fundamental math concept called the factor theorem.
The factor theorem. Okay, refresh my memory.
Sure. Basically, if a polynomial px equals 0 when x is, say, z, then xz must be a factor of px. It must divide px perfectly, leaving no remainder. So Starks use this. Take the first rule, a0 is 1. In our polynomial language, this means fg0 equals 1, where g0 is the point corresponding to the start of the sequence.
Right.
So if the rule holds, then the polynomial fx1 must be 0 at x equals 0, 0.
Which means, by the factor theorem, that xg0 must perfectly divide xx1.
Exactly. And the result of that division, if it works out perfectly, must be another polynomial. We call this a constraint polynomial. Let's say p0x. If the original trace didn't start with 1, that division wouldn't work cleanly. You'd get a fraction, not a polynomial.
Clever. So you check if the result of the division is a polynomial, and you do the same for the final condition and the transition rule.
Precisely. The final condition, A1022 equals 23387755057, translates to checking if fx 23387755057 is divisible by xg1022. And the transition rule, n plus 2 equals 12 plus n2, gets turned into a polynomial identity involving fx, fgx, and fg2x, which must hold true for almost all points corresponding to the steps. This also results in a constraint polynomial, say p2x, if the rule holds everywhere.
So now we have potentially several constraint polynomials, p0, p1, p2, and each one should have a reasonably low degree if the original computation was correct.
That's the key. If the original trace was valid, all these constraint polynomials derived from the rules will themselves be well-defined polynomials of a relatively low degree.
Okay, but checking multiple polynomials sounds like maybe inefficient.
It could be. So Starks do something really smart here. To make things incredibly efficient, instead of checking these, say, 3 separate constraint polynomials independently, they combine them into a single master polynomial called the composition polynomial, or CP.
The composition polynomial, okay.
How it works is the verifier randomly selects some coefficients. Let's call them alpha, alpha1, alpha2. These are just random numbers chosen by the verifier.
Right.
And these random alphas are used to create a weighted sum of the individual constraint polynomials. CPx equals alpha 0, 0x plus alpha 1p1x plus alpha 2p2x.
Ah, I see. So the beauty of this composition polynomial, if I'm getting this, is that by combining them with random weights, we get to do one big check instead of lots of small ones.
Exactly.
And if the big one passes, the randomness makes it overwhelmingly likely that all the little ones must have passed too. That's really clever.
It's a cornerstone of Stark efficiency. If the original trace is valid, then all the individual polynomials are low degree, and therefore any random linear combination of them, the composition polynomial, is also guaranteed to be a low degree polynomial.
And the prover then commits to this new composition polynomial using another Merkle tree.
Right. Precisely. Another commitment, another Merkle root, is generated and sent to the verifier.
Okay. This brings us to the next big challenge, doesn't it? How do we actually prove that this composition polynomial, the CP thing, is indeed low degree? Because that implies all our original rules were followed.
Right. And that takes us to part 3, proving closeness to a low degree polynomial using the FRI protocol.
But here's a subtle yet really critical point you mentioned earlier based on that discussion source. Starks don't necessarily prove the CP is exactly a low-degree polynomial, but rather that it's close to one. What does closeness actually mean here?
Good question. Think of it this way. The distance between two functions is simply the number of points where they disagree. So if a function f is close to a polynomial p, it just means they disagree on only a small, sort of negligible fraction of points in that large domain we evaluated on.
Okay, so not necessarily identical everywhere, but very, very similar.
Exactly. And this closeness is proven using a really powerful component of Stark's called the FireEye protocol. FireEye stands for Fast Read Solomon Interactive Oracles Proof of Proximity.
Wow, that's a mouthful. FRI protocol.
It is. But the genius of FRI isn't just about reducing the degree, which it does. It's the interactive and probabilistic way it lets a verifier become convinced that a function is close to a low-degree polynomial with overwhelming probability, even without seeing the whole thing. It's truly a proof of proximity, and it's fundamental to Stark's scalability.
Okay, so interactive. How does this interactive process actually work? What do the prover and the verifier do?
It's this fascinating back and forth cycle. It starts with the approver committing via a Merkle tree to the current polynomial initially, our composition polynomial.
Okay, commit first.
Then the verifier sends back a random challenge value. Let's just call it beta.
A random number, beta. Got it.
Now the prover uses this beta and applies what's called the FRI operator to their current polynomial. It's a bit mathematical, but imagine you can split any polynomial px into two simpler parts. An even part g, x2, and an odd part xx2.
Okay. Even in odd parts based on powers of x?
Kind of, yeah. So px equals gx2 plus xx2. The FRI operator then cleverly combines these two parts, g and h, using that random beta challenge from the verifier. It creates a new, simpler polynomial by basically doing pes plus beta y, where y x2.
Whoa. Okay, so it mixes the even and odd parts using the verifier's random challenge. What does that achieve?
The crucial thing is that this new polynomial, mu, has roughly half the degree of the original polynomial p.
Half the degree. Okay, that's significant.
It's like taking a complex song, as we sort of alluded to, reducing it to its core melody, then maybe to a single repeating note step by step. But the verifier's random beta ensures this reduction is done honestly.
And this process repeats.
Yes. The prover commits, via another Merkle tree, to this new lower degree polynomial, nu. The verifier sends another random challenge. The prover applies the FRI operator again, having the degree again.
I see the loop.
This cycle continues. Commit, challenge, reduce degree, commit, challenge, reduce degree, until the polynomial's degree is reduced down to something very small, like a constant or degree 1, something trivial to check.
And importantly, each step involves new Merkle tree commitments for these successively lower degree polynomials.
Absolutely, a whole sequence of commitments.
Okay, so we've encoded, constrained, combined into a CP,
Okay.
and then iteratively reduced it with FRI, committing at each stage. Now, how does the verifier actually check all this? This must be part 4. The proof, decommitment, and verification checks.
Exactly. This is where the rubber meets the road. The prover has made all these commitments. Now they have to convince the verifier they were all truthful. This is the decommitment phase.
How does that work? Does the verifier ask for specific things?
Yes. The verifier doesn't need everything. They send a small number, let's say q, of random elements or queries chosen from that large extended domain we talked about way back at the LDE step.
Just a few random spots on that big curve.
Exactly. And for each query point, say z, the prover has to provide two things. First, the specific value of the polynomial at that point z. This is a leaf from the relevant Merkle tree commitment.
Okay, the value itself.
And second, its Merkle authentication path.
Ah, the proof that this leaf value actually belongs to the Merkle root commitment they sent earlier. Like getting that single page from the book, but with the stamp proving it's from that specific edition.
Perfect analogy. It cryptographically links the revealed value back to the original commitment.
Now, this brings us to that crucial insight from the Muhammad and Jake chat you mentioned.
Yeah.
The verifier doesn't need to know all the leaf values in the Merkle tree beforehand, right?
Correct. That's super important. The verifier only needs the value at the queried index Z and the cryptographic proof, the Merkle path, that it's consistent with the root they already have.
So what does this mean for someone actually doing the verification? It means the verifier doesn't need the answer sheet in advance. They can check correctness just based on these random probes.
Precisely. The verifier performs two main checks for each query. First is the value, or values, because they check consistency across FRI layers too, provided by the prover consistent with the pre-agreed algebraic constraints and the FRI reduction steps.
Okay, does the math check out for this specific point?
Right. And second, does the Merkle proof confirm that this value was indeed part of the prover's earlier commitment, the Merkle root?
So the math works, and the value is authentically from the commitment.
If both checks pass for a sufficient number of random queries, the verifier becomes highly confident that the prover did the computation correctly and honestly followed all the protocol steps.
And it's important to remember, right, that the constraints themselves, the Fibonacci rule in our example, aren't secret. They're public knowledge.
Absolutely critical point. These rules are publicly known and agreed upon, just like in SNARKs. They are not hidden. The verifier can actually recompute the expected relationships between values at queried points based on these public rules. There's no blind trust needed for the rules themselves.
Right, that public verifiability is the foundation everything else builds on.
It is.
So finally, the verifier uses these queried values and their Merkle paths to check everything layer by layer.
Yes. They check the correct transition from the initial trace polynomial commitment to the composition polynomial commitment using the values provided for the queries.
Making sure the constraints were combined correctly at those points.
And then they check the correct transitions between each successive layer of the FRI protocol commitments, making sure the degree reduction happened consistently and correctly according to the random beta challenges at those queried points.
Wow. It's a very intricate but very clever series of checks based on just a few random samples.
That's the magic of interactive proofs and cryptographic commitments working together.
Okay, as we get into our final segment, let's bring it all together. Part 5. Stark versus Snark strengths, weaknesses, and future implications. This is where we distill, why you might choose one over the other and what kinds of problems Starks are maybe uniquely positioned to solve.
Right, so the first major differentiator, as we touched on, is transparency. Starks are inherently transparent.
Meaning no trusted setup required.
Exactly. That eliminates a potential point of vulnerability or a trust assumption that's often present in many types of snarks, which might require a complex, secure ceremony to generate initial parameters.
And that's a big deal for public decentralized systems.
Huge deal. And related to that, as we also mentioned, Starks are generally advertised as quantum resistant.
Because they rely on hashing and symmetric cryptography, not the elliptic curves or pairings that quantum computers could potentially break.
That's the idea. They avoid the specific mathematical structures known to be vulnerable to Shor's algorithm, for instance. Snarks, which frequently use those structures, face this challenge looking towards the future.
Okay, what about performance? Proving time, proof size, verification time.
Good question. Starks generally boast pretty good prover computation time. It's often quite efficient to generate a Stark proof.
Okay.
However, when you look at the size of the proof itself, Stark proofs are usually considered moderate or maybe even large compared to Snarks. They scale roughly as O log squared n, where n is related to the computation size.
Whereas Snarks are famous for having tiny, constant-sized proofs sometimes.
Often, yes. Snarks can achieve very small, sometimes constant proof sizes, which is a major advantage for things like blockchain space.
And verification speed, checking the proof.
Both are generally fast to verify. Snark verification is often described as very fast. Stark verification is also fast and scalable, meaning the time to verify grows very slowly, polylogarithmically, with the computation size, which is excellent.
So if we connect this to the bigger picture, the key insight seems to be that Starks consciously trade off having the absolute smallest proof size in exchange for that fundamental transparency, no trusted setup, and future-proofing against quantum computers.
That's a great way to put it. This makes them particularly appealing for applications like long-term, trustless infrastructure, think public blockchains, verifiable computation platforms where avoiding a trusted setup is paramount, and quantum resistance is a serious long-term consideration.
Even if the proofs are a bit bigger today.
Even if the proofs are a bit bigger. And it's worth noting, too, the discussion sources touched on potential implementation subtleties.
Ah, yeah, the point about the random alphas.
Exactly.
Yeah.
Like the randomness of those alpha coefficients used to build the composition polynomial. If they aren't truly random, perhaps predictable by a malicious prover,
Oh.
they might, in theory, be able to craft a composition polynomial that looks low degree, satisfying the verifier's checks, but actually hides incorrect individual constraints. Maybe by cleverly making the non-polynomial error terms cancel out.
So the implementation security matters just as much as the theoretical soundness.
Absolutely. It highlights the ongoing challenge of building robust cryptographic systems in practice. The theory is elegant, but making it work securely requires careful engineering. It's a field that's constantly evolving to address these kinds of potential issues.
Fascinating. And that really wraps up our deep dive into Starks. We've navigated quite a journey here, from encoding computations into polynomials, committing with Merkle trees,
To arithmetizing constraints, building that composition polynomial,
proving closeness with the incredible FRI protocol, that iterative degree reduction.
and finally, the decommitment and verification checks using random queries and Merkle paths.
Yeah. And we've seen how Starks offer these unique advantages, especially transparency and quantum resistance, as really key differentiators from other ZK-proof systems.
Definitely. And maybe as we conclude, just something to think about. Consider the profound implications, specifically of Stark's transparency and quantum resistance. How might those specific features fundamentally reshape trust models? Maybe in decentralized finance, making it truly trustless long-term. Or perhaps making data auditing in, say, cloud computing genuinely unassailable, even against future quantum threats.
It's not just about proving anymore. It's about proving without compromise, without hidden assumptions or future vulnerability.
Exactly. That's the potential power here.
It's a truly mind-bending concept, and one that's clearly already reshaping parts of our digital landscape. Thank you so much for walking us through that.
My pleasure. It was fun to dive in.
And thank you all for joining us on the Deep Dive.